So let me start with the system I would like to discuss. So the following system of equations, so as you may see, we have a little bit more equations than in the morning session. Actually, this system is not very popular among the students because there are simply too many equations. But you may guess what I'm talking about. So everything will take place. So this is a very simple model, actually, of a fluid, which is a sort of complete from the point of view of thermodynamics, which means that we have somehow, the fluid is compressible. It is viscous, so there is something like viscousness in the equations. And the fluid also changes temperature and the density and of course velocity. So there are basically three unknowns in the system. And we are going to discuss solutions of this problem. So in particular, we have the entropy equations here. So S is called the entropy. And so which is somehow representative of the second law of thermodynamics. And there is also conservation of the total energy. So this quantity here, so I don't think I should spend some time on explaining the meaning of the notation because either you are familiar with this or it doesn't make too much sense. Anyway, so this is my problem. So there are two aspects. So first aspect is that the system is dissipative because there is some kind of equation for the entropy. And on the right-hand side of the entropy equation, we have sigma. Sigma in the future will be a non-negative quantity, a measure. And so this means that the entropy is being produced by the motion or by the evolution of the fluid. So there is second law, so the system dissipates energy, but not the whole energy, because the whole energy, the total energy should be conserved. So in this problem, there is nothing like energy inequality. We have really a total energy balance. There is no, for simplicity, I did not include any driving forces nor sources of heat energy in my system. And so I assume simply that the total energy of the whole system is conserved. So this E here stands for the internal energy of the problem. And so there are both aspects like dissipativity and conservation included in the system. And in my talk, I'll concentrate, in accordance with the leading topic of this conference, to some asymptotic behavior of the fluid, limiting behavior of this fluid. So in the future, there will be some parameters that will characterize the motion, and these parameters, in certain cases, will become either infinite or small. So I'll be talking, at a certain part of my talk, I'll be talking about what is called singular limits. And so the leading idea of this talk is the study or the principle of stability. So we have seen in the morning, during the lecture of Isabel, that actually it is useful if we compare solutions of our problem with something what we know. So basically, all these beautiful results, which we have seen, were based on a very simple idea. Of course, the proof was much more involved, but the idea was that we have some known object. In the case of Isabel, it was the known solution of the problem, and we somehow study how far our solution may go from this object. Huh? So if you push this idea forward, you may think, why should I study how far is the solution from a known solution of the problem? Maybe I can take any trajectory, any whatever, not even solution of a given problem, and I may study how far, and I may characterize my solutions by the fact how far they stay from a given object. And so that's the idea behind the theory of relative entropies, or in my talk, it's more appropriate the name relative energy, because actually the dimension of this quantity is going to be energy. And so I will show you that this can be, such a quantity can be indeed introduced for this system and can be useful in the studies of questions like, for instance, weak-strong uniqueness, singular limits, as well as the behavior of the problem when certain parameters become zero or infinite. Okay, so this is a nonlinear system. All these functions are nonlinear, so you may guess it is difficult to prove the existence of smooth solutions for any given time interval. So throughout all my talk, I'll concentrate just on the weak solutions of this problem, and I'll assume that they exist. There is indeed, for this setting, you can develop some kind of existence theory under certain restricting assumptions concerning the pressure and also on the heat flux, but I don't want to talk about this problem here. So maybe I just should say, okay. Okay. So maybe I should mention for definiteness that we have some constitutive relations. So first of all, I assume the usual Gibbs law between which relates the internal energy, the pressure, and the entropy. We assume the fluid is Newtonian, so we have a linear dependence of the viscosity on the velocity gradient. These coefficients in the future are allowed to depend on the temperature. At least this is allowed by the existence theory. We also assume that the heat conductivity is given by the Fourier law. And we assume, our formulation of the second law of thermodynamics is that the function sigma we have seen on the right-hand side of the entropy production is a non-negative quantity, which is bounded below by this. So if you are familiar with the classical formulation of the problem, you know that actually in the classical formulation, the entropy production should be exactly equal to this expression. Well, in the weak formulation of the problem we are using, actually, we allow the entropy to satisfy inequality. So that's why we augment the system by an extra assumption that the total energy is a conserved quantity. And if you combine these properties, you can easily show the following thing. If you have a weak solution of the problem, which means all relations are satisfied in the sense of distributions, including the entropy inequality, and if you in addition know that your weak solution is smooth, then you can show that actually you get equalities here. So it's a good concept of the weak solutions. Another advantage of this concept of weak solution is that, as I said, we can prove, that's a joint result with Antoni Novotny, who is sitting over there, we can prove that under certain circumstances the weak solutions exist globally in time. So we have some objects to deal with. Okay, so what is the concept, or what is the principle of relative energy or entropy functional? So there is some common structure. So we take some functional, which is a functional which depends on two things, on two triples, if you want. On the left-hand side, we have the triple which represents the weak solution of the problem. So this is rho, theta, and u is a weak solution of my problem. And on the right-hand side, we have another trio which could be, I mean, in my talk, it's going to be arbitrary trio of sufficiently smooth functions. And these functions maybe not really correctly, can be also called like test functions. And we would like to find some relation. We would like to find such this functional so that the following properties are satisfied. So there are several properties that should be satisfied by this functional. The first one is that it measures somehow the distance between this trio, which represents the weak solution of the problem, and an arbitrary trio of smooth functions. So it should be always non-negative, but it is zero if and only if these functions coincide. So which means that this gives me some kind of, I'm not saying that this functional has some other properties of the distance, but at least I know that if this quantity is zero, then then these two functions or these two trios, these two quantities must be the same. Well, there are some other properties that should be satisfied. It should be a kind of Lyapunov function for the problem. Which means that now we are really working not only with some arbitrary trio of functions, but we take a very special choice. Our choice is the equilibrium solution of the problem. So what we require is that this function, if you plug in place of these test functions, if you plug in the trio which consists of equilibrium solution, which in my case, of course, the equilibrium solution depends on the boundary conditions. As I said, in my case, I didn't say that, but in my case, I'll concentrate on bounded domains, which is the physical case. So there will be nothing like the whole space. Well, there will be whole space later on. But for the time being, we consider a bounded domain, omega, well, sufficiently smooth in the three-dimensional space, and you have noticed on the first slide that there are some boundary conditions. And so under these boundary conditions, there is a very simple equilibrium solution to this problem. By equilibrium means solution which doesn't change in time. In this case, it is just that rho bar is a constant, theta bar is a constant, and actually the equilibrium solution is zero. But you may think about a general situation that you have an equilibrium, a solution which doesn't change its time, and you require your E, your relative entropy, to be, or your relative energy in the future, to be a Lyapunov function. Well, the second property is, which is actually quite important if you want to prove results like weak-strong uniqueness, which means if you compare your solution, your weak solution, to another solution of the same problem, which happens to be smooth. then you require a kind of ground wall inequality, right? So you require your E to be chosen in such a way that if you evaluate the difference of the value of E between two times, then it is less or equal the integral from T1, tau1 to tau2, which is integrated over this time, times some function maybe, which is L1 on 0t, times the value of this relative entropy. So if you have this, and this should be true, okay, you don't expect this to be true for any trio of smooth functions, but it should be true for any smooth solution of the same problem. Then you see that if you happen to take, so of course in this assumption it is hidden that the smooth solution exists, but for the time being we just assume that it is the case. If it's not the case, just this assumption is empty. And so if you use this inequality, you may prove, and if you have such a function, you may show what is called weak strong uniqueness. If it happens that you have a strong solution of the problem which starts with the same initial data, then we know from the previous property that actually if you take tau1 to be the initial time, then this quantity is 0. Then you can use ground wall lemma in order to conclude that actually these two solutions will coincide also in the future. So these are the basic properties of the relative. So in the literature, at least what you can, or what we could find, are results which always, in all particular case, people take this relative entropy or relative energy, if you want, and they plug in some special function. So our idea was to have a general relation which will somehow include all these cases, and later on we were hoping to apply it to some specific problems, and I think also Antonin will talk about some other applications of this method. So now you may wonder what would be a good relative entropy for my system. Okay, so what is the relative entropy for the Navier-Stokes-Fourier system? So actually the way we obtain it was a bit non-standard, at least for people who work in the theory of hyperbolic conservation laws. I'll make the remark at the end of this slide. So actually what we did was that we first found the Lyapunov function. The Lyapunov function for this problem is the so-called, well, the name, don't ask me why this is the exact, I mean, why this is a proper name for this quantity. Actually, at the beginning, we call it Helmholtz function. This is a quantity which is composed of two things. There is internal energy and there is entropy multiplied by capital theta. At the beginning, the capital theta was just a constant. If you go back to my system, now we know that if you take the integral of this quantity, so the first thing, plus some kinetic energy, doesn't change the sign. And the second thing, if this is a constant, is being produced. So this is actually a kind of a good candidate for a Lyapunov function. And indeed, you will find out, and that was actually the first application before we started to study this, I mean, in a more general context, was that this function provides you a kind of Lyapunov functional for the full system, which means if you take the equilibrium solution, this is really a Lyapunov function. So this is a function which is constructed by means of this. The first one is like the kinetic energy. So it is also this relative, that's why I call it relative energy, because it's actually the dimension of this quantity is energy. So the first term represents the deviation of the energy, of the kinetic energy of your solution, between your solution and maybe some given function. In the first application, as I said, the U was taken to be 0, which corresponds to the equilibrium solution. And the second thing is almost the same thing as we have here, but we assume that this is a sort of linearization of this quantity around the state R, right? So you take this quantity, you compute the derivative, and you subtract it. And it turns out, because this function turns out to be convex, at least if the so-called thermodynamic stability hypotheses are satisfied, which means if the pressure is an increasing function of the density, then this function turns out to be convex with respect to rho. And so this is actually a good candidate for the relative entropy, because indeed you can show that this function is 0 if and only if these two triples coincide, and it is positive elsewhere. And so this, of course, we don't know if we have the other properties because they somehow depend on the character of the problem. But we just use this function as a Lyapunov function, and it turned out that it is also a good candidate for this relative entropy. Of course, now when we discuss this problem with people working in hyperbolic conservation laws, I was told, yes, but actually that's something what is well known to people. Actually, Constantin Dafermos, a long time ago, proposed something what I would say is very similar to this functional for the Euler system, for the system where you have also that there is no viscosity, but there is temperature and there is density, so it's a compressible fluid with changing temperature. He proposed something like which was based on real entropy. I mean, you take the entropy which is associated to the system, you linearize it around a given state. But actually it turns out finally that the Dafermos entropy and our entropy differ by the factor 1/θ here, which proved to be quite useful in applications, because when you apply it to our system, to the system with diffusion, the fact that there is a factor 1/θ between these two entropies makes this entropy more convenient. Actually, you can show that this entropy can be somehow employed in connection with the weak solutions of the Navier-Stokes-Fourier system, at least with the weak solutions we can construct or that are known to exist. While if you add this factor, you will find out that this is not actually, in order to work with the same relative entropy multiplied by this factor, you will have to have something like the equation for the total energy of the complete fluid system. And as far as I know, I mean, the existence theory does not cover the case where you can really derive the equation for the complete energy. So this factor, at least for us, made a big difference. Secondly, also, if you go through the proofs of some results I will be discussing later, then actually you would find out that if you if you replace the balance of entropy by the balance of total energy, the expressions will become much more complicated. Because this is just the beginning of the story. Now you have to verify that actually this new function really satisfies the properties you would like to have. And it is actually quite easy to check that this is a Lyapunov function. But the second property, meaning that it satisfies a kind of Gronwall inequality for any smooth solution of the problem, is much more involved. Actually, what we derived was something so it was something more general. So I deliberately omitted the explicit formula for this quantity on the right-hand side because it looks terrible, but actually it can be computed. And so what we derived was a kind of what may be called relative energy inequality. So that's something what we have seen on the second slide. So we evaluate or we compare the value of the relative entropy between two times. And it turns out that it is actually dominated by some remainder term, which can be computed explicitly in terms of time and these two quantities. And actually it turns out also after some work and several pages of work that this term is actually dominated by some integrated function, by some integrable function of t times the relative entropy itself, provided we take this trio to be a smooth solution of the same problem. So of course, in order to derive this relation, you need to work with the equations. And because we wanted to work with the weak solutions, you must make sure that actually you can compute the time evolution of all quantities or the time changes of all quantities that appear in the relative entropy in terms of your weak solutions. And so I made a list of the quantities which appear here, and actually I would like to convince you that all these quantities can be computed also in terms of the weak solutions, which means it is enough to know only the equations satisfied in the sense of distributions. If you go through the formula for the relative entropy, you will find several things to compute. So if you want to evaluate this, you will find, first of all, you will find the total energy. The total energy, because there is E plus the kinetic part, so you will find an expression like that. Well, for this expression, you have the energy equality actually, so you know what it is, so you can compute this. Now the second term you will find out, because you remember in the relative entropy there was something like theta, where now theta is no longer a constant, but it's a function, it's a smooth function. So there is an expression which looks like the entropy tested by the function theta. For this expression, you have the entropy inequality, which is computed in terms of distributions, but still you can compute this. Now where this term comes from, you remember there was in the relative entropy there is actually not the energy, but something like perturb energy. So there is a term which looks like 1/2 of rho u minus u square. And so you will find out that, well, apart from the energy, you also get a term which looks like rho times u. So you have to somehow to compute the rho u times small u, right? So you have somehow to be able to compute the evolution of this term in terms of the weak solutions of the problem. Again, you will find it in the momentum equation. So this term here, you can find it. You can use the weak formulation of the momentum equation, supposing that this quantity is actually smooth. Then you can compute this quantity from the momentum equation. So you know what is the time evolution of this quantity in terms of the momentum equation. Finally, we have seen that here what we get is also rho u square, where rho u square is a capital U, again, is a smooth function. So in order to evaluate this, you have an expression which looks like rho u square. Again, this is a smooth function, so for this you can use the weak formulation of the continuity equation. Again, you know what is the time evolution of this integral. You can just use the weak formulation of the problem. There are several other expressions which can be sort of put together in this function g. And so you realize at the end of the day that actually you have to take care of expressions that look like this function rho multiplied by some smooth quantities. And so all this can be evaluated by means of the equation of continuity. So actually it is possible, at least hypothetically, to compute really in terms of the weak formulation of the problem all quantities which appear in this difference, and this gives you this term on the right-hand side. So we have this relative entropy inequality. Now let me point out again that these functions R, theta, and capital U, we don't assume anything about them. The only assumption is that they are sufficiently smooth in order to compute all the integrals that appear in the weak formulation. And the second property is that, of course, you have to be able to take them as test functions in your problem. And so they must satisfy, in particular, U must satisfy the appropriate boundary conditions. So as you know, for the velocity u, you can take different kind of boundary conditions. In my talk, at least on the first slide, I didn't comment on that, but I take Dirichlet boundary conditions, or what is called no slip. You can take also complete slip. It doesn't change so much, but you have to keep in mind that this test function must be taken satisfying the relevant boundary condition. Otherwise, you wouldn't be able to use it as a test function in the formulation of the momentum equation. Okay, so that's what we have now at hand, and now let me show you some applications of this inequality. Okay, so the first one I already mentioned, it's a joint result with Antonin, and this is the so-called weak-strong uniqueness property. So you take a weak solution of the problem, in the sense on the first slide with energy inequality, with entropy inequality satisfied in a weak sense, and with the total energy balance. And you may ask what happens if you take, so you start with smooth data, and you may ask what happens if you take the weak solution and at the same time the strong solution. So the strong solution of this problem was constructed, at least locally in time, by several people. I think in this context the most relevant reference is a paper by Alberto Valli, where he could show that for sufficiently smooth initial data, the full system exactly in this setting with the hypothesis imposed on the transport and thermodynamics functions, and for sufficiently smooth data, you get local existence of smooth solutions on some maximal time interval, 0t max. Now you may wonder, so this weak solution looks like a very smooth one, very weak one, which means that actually we assume instead of entropy equality, inequality, and so on. So you may wonder if our weak solution, for the same data, of course, we can show that there is a weak solution of the problem. Now you may wonder if these two coincide. Well, it turns out that it is really true, because, and this is the first application of the relative entropy inequality. So you can wonder how you do it. You may somehow, oh, sorry, you may now see how you do it. So you take as the trio of test functions in the relative entropy inequality, you take the smooth solution and you just play with the term on the right hand side, which means some effort. But at the end, everything ends up very good, very well, and you get weak strong uniqueness. Well, using the first result, you may think about something what may be called conditional regularity of the weak solutions. We have seen many talks this morning where actually people tried to derive some conditions, at least actually in the context of incompressible Navier-Stokes system, when if you have some extra piece of information concerning your solution, you know that you have a weak solution, and suppose that you know something more about your weak solution, and you would like to say that automatically your weak solution is a smooth one. Here the problem is not that simple because there is no smoothing effect, so you don't hope to get any kind of Serin's condition here. You cannot hope to say, I have a weak solution, I know the velocity is regular, so the solution is regular. Because it turns out that the data, to begin with, the data must be regular. So if you start with the density, which has a jump, then as was proved by David Hoff, actually this jump will be there forever, and you wouldn't get rid of this jump, so you would never get a regular solution. However, you may ask what happens if you have a regular solution. So you start with regular initial data, and you may ask what should be satisfied by the weak solution in order to say that actually the weak solution is regular. And well, the criterion is here, it's probably not optimal, and at least for people who are familiar with Serin conditions and other refined criteria for the problem, you may say that this is very strong, but actually at least it's something. So assume that we have a weak solution which starts from nice initial data, and assume that you can control the gradient of the velocity in the L infinity norm, which is quite strong. But then you're done. Then your solution must be actually smooth. Huh? Although the weak solution satisfies only inequalities, if you have this, you get a smooth solution of the problem. And there are two parts. This is slightly different from what is normally called blow-up criteria for the full system. There are several papers where you can find the results which are sort of better than this, in the sense that the conditions are less restrictive. However, they always apply to some to strong solutions of the problem. So you assume you have the system, and usually people take very simple constitutive equation, for instance, perfect gas law, constant, and this is the main point, constant velocity and constant viscosity. Then you can get blow-up criteria for smooth solutions of the problem. However, they are not blow-up criteria for the weak solutions because the weak solutions are not known to exist. So because we wanted to have the situation when we know that the weak solutions exist, we had to include the case when both viscosity and heat conductivity depends on the temperature, and this somehow made some kind of extra difficulties. So actually what you do is that you prove this criterion, this blow-up criterion for your strong solution, but from the first result you know that strong and weak must be the same if they start from the same initial data, and so actually automatically this criterion is applicable also to the weak solutions about which you know that it exists. So that's a joint result with Yong-Johnson from Nanjing. Okay, so these are the first two applications. Maybe there are some other applications. Up to now, I said I would like to have something more general than just comparing two solutions of the same problem. But these are like results where you really use in the entropy inequality two solutions of the same problem. So another application is the problem. Now we are coming to the asymptotic behavior or limit behavior of the system. You consider something what is called scaled Navier-Stokes-Fourier system. So now again we understand the weak solution in the same way as before, but you do some scaling. So you can do several kinds of scalings. This is the scaling when you put several characteristic numbers to be either small or large. So you may recognize that, so in the pressure, in front of the pressure term, there is 1 over epsilon square. So this epsilon here plays the role, this is the Mach number actually for the problem. Well, there is a small term in front of the viscosity, so this is like the high Reynolds number limit. And we also scale, now I put some right-hand side, which depends on force which is acting on the fluid. In most of the examples, this force is like a gravitational force which acts on the fluid. And it is also scaled, so it is actually in the limit. As you may guess, epsilon will be 0 in the limit, so this right-hand side will be a large force, but not so large compared to the Mach number here, or not so small. This epsilon square is definitely smaller than epsilon here. And we also scale the heat conductivity here with some epsilon to the power beta. And in the entropy production, we get the corresponding scaling. This scaling here is not some extra new scaling. This just comes from the fact that we scale the Reynolds number and Mach number in the same way. Now you may wonder what happens in the limit. So what you would expect is that actually, well, the viscosity will disappear. So the limit will be, and the same, okay, provided alpha is greater than 0, what you may suspect. And beta, but if you also take beta greater than 0, so these two terms will disappear. So in the limit, we expect to get the Euler system. And in addition, because there is a low Mach number, this is the low Mach number limit, so the fluid will become, or should become, incompressible. The speed of sound tends to infinity, so in the limit you would expect to get incompressible Euler system, and because of this scaling here, you would get, or you would guess at least formally, that the limit system should be something what is called Euler-Boussinesq system. So it's going to be a system which is actually on the next slide, and it is the system which is written down here. So, we have the incompressibility condition, the Euler equation with some force on the right-hand side and with some temperature which satisfies this equation here. And of course, as I said, this theta bar and rho bar stand for the equilibrium values of the temperature and of the density. So there are some tests. So this is a result which can be proved rigorously. By using the technique of relative entropies, is relative energy. Again, it's a result with Antonin. So we need some technical assumptions concerning the coefficient alpha, which scales the Reynolds number, and the coefficient beta should be just positive. And now the way you apply the relative entropy inequality is that in place of the smooth quantities, of the quantities R, theta, and U, you plug in the quantities which corresponds to the limit solution. Now, of course, you have to assume, and that's somehow necessary condition here, that the limit system actually has a smooth solution, which we know that it is true on a short time interval, provided you take reasonably smooth initial data. But of course, it is not known to be true on an arbitrary interval. So the result of convergence is conditional. We get it on a short time interval, but this shortness is given only in terms of the lifespan of the smooth solutions of this problem. Actually, at the end of my talk, I'll show you that if you consider weak solutions of this problem, or some kind of weak solutions, then the result is probably not very likely to be true, because there are simply too many weak solutions to this problem. Okay, so that's the first, I would say, little bit non-standard application of the relative energy or entropy, because you take not, as a test functions, you take solutions of the limit system. You can imagine that you can use the same technique for other kinds of limit problems. In particular, that's another result I would like to discuss a little bit. It's the problem of rate of convergence in the singular limit problems. Because up to now, so we know that we have convergence to the limit system, but we don't know how fast. Sometimes it is important also to know how fast your solution actually converges to the limit problem. So as an example, I take a simplified system. I don't consider the temperature now, because I would like to speak about the results we were able to prove. I'm not saying that it cannot be done for the full system, but let me concentrate on some simple situation, which is just scale compressible Navier-Stokes. So I forget the temperature for the time being, and I take a bit simpler scaling here. I take the scaling, which consists of taking a low Mach number here, again, so in the limit, again, you would expect the system to become incompressible, and I take small viscosity, or high Reynolds number, which is now represented by the number nu here, and I consider something what I call large physical space, which means that, well, as we have seen in certain applications, in particular in mathematical treatment of problems in fluid mechanics, it is good to work on the whole space R3. However, you may think that the whole space is not really physically relevant because, well, I don't think that any reasonable physical problem is posed on the whole space. However, you may think in terms of the domain to be large, which means that, okay, you are not working on the whole space, but you are working on a domain which expands. So for simplicity, you can take a domain which you take a fixed domain and then you just blow it up by some factor m here, which is what is written down here, and you impose, for instance, the Knowsley boundary conditions on this domain. Now, what is the advantage of this blowing up the domain? that you may hold that in the limit process, actually your solutions, in particular the solutions of the associated acoustic equation, will behave, or at least on the lifespan you are interested in, they will behave like solutions of the problem without boundary. Right? So you may consider this problem, which in my opinion is a kind of reasonable approximation of what is called like R3 domain, is a problem on a large domain. And now you may wonder what happens. Again, you may expect that in the limit, these solutions of this problem will tend to now in this case, because there is no force, you expect to get incompressible Euler equations on the whole space, because in the limit, when m will be a large parameter here, so in the limit, the limit will be defined on the limit system will be defined on the whole space. Well, so that's what I call target system. So actually what we assume is, well, I call it path hypothesis. It's not really, there should be nu here, I'm sorry. This is not u, but nu. This is the viscosity. That's not u. So so you assume some kind of, it's not, I mean, these quantities do not tend to zero in an arbitrary way, right? So you assume, well, you assume the Mach number tends to zero, you assume the viscosity, this is the viscosity, I repeat, tends to zero, but you also assume this condition here, which means exactly what I said before, and it is connected with the equation which is written down at the bottom of the slide. So actually, I assume that the radius of my domain goes to infinity much faster than epsilon goes to zero, which is somehow related to the speed of the waves of to the speed of solution, or to the propagation speed of solutions of this, what is called acoustic equations. Because in this problem, there are two aspects of the limiting behavior. One is that, well, the velocity consisting of two parts at the beginning. So for the primitive system, for the starting system, I have velocity which has both compressible part, which is represented by the gradient, and the incompressible part, which is represented by some solenoidal function. Actually, what you expect to see in the limit is to only the solenoidal component. So this is the limit incompressible system. But of course, there is also this acoustic component which should disappear from the system. If you do formal analysis, you will find out that actually these acoustic waves, they satisfy this kind of what is sometimes called Light-Hill's acoustic equation. Well, okay, I just, for simplicity, I omitted the right-hand side, but actually the behavior of this of the gradient component of the velocity is actually governed by this acoustic system, which is scaled by epsilon. So actually, now you are interested in the behavior of these waves at a long time, and so we know that well, the speed of propagation is just proportional to 1 over epsilon. So if this m goes far, I mean, if the radius of domain will be very far with respect to the speed of propagation for this problem, actually this system, at least on some fixed time interval, would not see the fact that the domain is bounded. And in the limit, you can describe everything by solutions of this problem on the whole space R3. Well, of course, the obvious advantage of considering this problem on R3 is that there is a dispersion effect for this problem. This problem, from this point of view, is very simple. It's just a linear wave equation for which you get, if you want, local L infinity decay, provided the data are reasonable, which means that in the limit, actually, these acoustic waves will not bother you, and you can pass to the limit. Okay, but now you may wonder how fast you pass to the limit, and actually, okay, I'm sorry. Actually, if you use, so you can use the entropy, the relative entropy technique, which gives you really the rate of convergence to the limit system. So you start with something what is called ill-prepared initial data. But actually, we are not assuming anything about that epsilon is small, or nu is large, whatever. Now you take, so you take the initial data in this form. So you take some constant state plus epsilon perturbation by some function, and you take the initial velocity. So again, so you can get the following. This is not really a convergence result. It's an estimate which tells you how these quantities are estimated in terms of the initial data and the value of these parameters. And again, the method is exactly the same as before. You take the limit system and solutions of the acoustic waves, you plug them in the relative entropy inequality because you know that they are smooth. And you compare it, and you get some extra term after some effort. You can basically compute what's going on. So what is here? So these are these two terms we know from the relative entropy. So we know, so now we see that actually U will be close to the limit function V minus the gradient phi, which is phi is the solution of the acoustic equation. So U will be close to the sum of these two things. So this is the limit function, and that's the acoustic component. I'm not assuming that the acoustic component is small or not. So you may like it or not, actually the acoustic component will interfere, is there. The same here, actually this quotient here will be close to Z. Z is the solution, is the second component which appears in the acoustic equations. Well, the distance is measured in some L2 norm. Here there is gamma, which is related to the coefficient gamma in the pressure law, which I didn't mention probably. And you will find out that this is actually dominated by these two things. This is related to the initial data. So we are not even assuming that the initial data are in some sense close to the limit here, right? We are just assuming that this is a finite number. So this you may see as a kind of approximation. This is a kind of Helmholtz decomposition of the limit, if there was any, of the initial data for the function U. And this is a kind of approximation, or how far is this function R from the function Z0, which is the initial state in the acoustic equation. So if these two things are small, we know that this will be small, and there is an extra term which is proportional to the scaling parameters. So it holds for any alpha, so there is a constant which blows when alpha approaches 1 here, but actually you can show that the distance is small, and the smallness is measured by the viscosity in the first power, epsilon to the power alpha, that's the Mach number, and this factor 1 over epsilon m epsilon, which somehow measures how far is how large the domain is. So you get a precise qualitative information how far is your solution from the limit system plus the acoustic component. Of course, now knowing that the acoustic component will disappear at least locally, you can use this result for proving convergence, but this gives you some kind of idea how fast the convergence is. Huh? So that's a joint result with Sharkanechasova, Yongzhon Sun. Again, the same Sun as in the conditional regularity. Well, finally, let me make a short excursion and this is probably the topic maybe Ondřej Kreml will speak about. That's what happens when we change the philosophy a little bit, because up to now we have been using the relative entropy inequality. And so in the relative entropy inequality, always the candidate for the target system, limit system, smooth system, was always some quantity which was smooth. I mean, that was somehow necessary, because otherwise we wouldn't be able to derive this relative entropy inequality. However, now you may ask, what happens if, for instance, in many cases, the limit system was the Euler system. And so you may ask, what happens if we deal with the weak solutions of Euler system? Well, you may say that the weak solution may not exist globally in time. However, the situation is not so bad. On the other hand, however, you will find out that in many situations the weak solutions are not really good candidates, because they become very unstable. In particular, and now we can also see the reason, they cannot be used as test functions in the relative entropy inequality. So let me illustrate it by a short example of what we call Euler-Fourier system, which, as you may see, is not exactly very physical, because we do two things. We just forget, so this is like the perfect gas law here now. We take a very simple system, and we forget viscosity in the momentum equation, but we still keep heat conductivity. So this should not happen for reasonable gases. However, let's make this assumption here, and let's consider this problem here. So this is it's a kind of mixture between say this kind of parabolic equation. There is some smoothing for the temperature, but this is like truly hyperbolic. I'm sorry again, there should be temperature here. It should be theta, not U. Oh, this is the perfect gas law. So the pressure should be rho times theta, not rho times U. Oh, here, this guy here. Okay. And so now you may wonder, so at the first glance it looks like, so now you may think, what about weak solutions of this problem? Because probably this system is not very likely to have smooth solutions, although there is some smoothing for theta, but there is no smoothing for rho and U. And at the first glance it looks like a hopeless task, because you know that, well, hyperbolic systems are difficult to solve. However, it turns out that actually if you think only in terms of existence of weak solutions, the situation is not so bad. You can show actually that is for this specific system, in this specific formulation, I deliberately avoid any energy inequalities and entropy inequalities. But if you formulate weakly this problem, means you put all derivatives on the test functions, you can prove the following result. That's a joint result with Elisabetta Chiodaroli and André Kremer. Actually, this problem, you take initial data. Surprisingly, you need the initial data to be smooth. Well, I don't know. I don't say how smooth. I would say 2 derivatives will do. Huh? You can show that for any choice of initial data, actually this problem has global in time solutions. On any time interval, you can construct global weak solutions. This is the good news. The bad news is that there are simply too many. There are infinitely many. So, well, these solutions are constructed by the method of convex integration. Laszlo will tell us something on Wednesday morning. However, this example shows that actually the weak solutions here are not very good in this business because there are simply too many. And so there is, it is not very, it is not expected that that solutions of in some asymptotic limit will converge to infinitely to some of these weak, well, that you can prove that you converge to some weak solution here. Well, so now we know, or at least some people know, that these weak solutions in many cases what we would call faked weak solutions, in the sense that they are producing energy. So you may wonder what happens if you impose as an extra condition some kind of energy conservation, or at least the dissipation of the total energy in this problem. It turns out that, of course, such a result is no longer possible, because for such kind of equations, for such kind of solutions, you can prove also Wikström uniqueness. So actually, if you know that the data are smooth, then you can show that the solution is unique. However, you can still construct solutions for any given rho and theta 0. You can find the velocity field, which is not regular in this case, such that the problem still admits infinitely many solutions which do satisfy in addition some kind of energy inequality. Okay, so I think it's time to finish. Thank you for your attention.